Today, we're really diving into one of the biggest bottlenecks in AI. It's this challenge of getting enough perfectly labeled data. It's often slow, can be incredibly expensive, or sometimes just, well, impossible to get those pristine data sets you need for training powerful models. But here's the exciting part. There have been some recent breakthroughs changing the game. We're going to explore four pretty ingenious techniques that kind of act as a shortcut. They let AI thrive even with limited hand-labeled data. Our mission: to quickly get you well-informed on efficient AI training without you needing to tag a single image yourself. Okay, let's break this down. So first up, let's talk about weak supervision. This one almost feels like cheating, doesn't it? But like in a good way. Instead of perfect human-generated labels, it trains models with data that might be noisy or incomplete or, just imprecise. The main idea is using what they call labeling functions, basically programmatic rules or heuristics, to automatically assign labels.
Yeah, exactly. And what's truly fascinating here is how it handles that old garbage in, garbage out worry. You'd think, okay, if the labels aren't perfect, the model won't be either, right?
Right.
Well, imagine in natural language processing. Say you want to find chemical disease relationships in just tons of text. A labeling function might just use a simple dictionary lookup to tag things.
Okay, but that sounds like it would make a lot of mistakes.
Oh, absolutely. Individually, these labels are often wrong. But the genius of weak supervision isn't relying on just one weak source. It's about combining multiple imperfect sources and then, crucially, mathematically modeling the noise and the conflict between them.
I see. So you're kind of figuring out how they're wrong together.
Precisely. You model the error patterns, and the result, surprisingly, is often a highly accurate set of labels, but scaled up to volumes you could never manage by hand.
Wow.
It's a real game changer. Turns massive amounts of cheap, imperfect data into something genuinely powerful.
That's incredibly powerful, making sense of the mess.
Okay, but what if you don't even have enough data to start with, noisy or not? That sounds like where semi-supervision comes in, offering a way to stretch the few good labels you do have.
Exactly. It combines a small amount of labeled data, the good stuff, with a much larger pool of unlabeled data.
Okay.
If we connect this to the bigger picture, semi-supervision often works based on some pretty intuitive assumptions about the data, like the smoothness assumption, basically. Points that are close together in the feature space probably share the same label. Makes sense.
Right, that feels intuitive.
Or there's the cluster assumption points that naturally group together in the same cluster likely belong to the same category. So these assumptions let the model make intelligent guesses about all that unlabeled data. It's like connecting the dots using what it learned from the small labeled set.
So it extends the reach of your limited labels without needing more direct human input. Clever.
Very clever. It boosts performance significantly sometimes. So semi-supervision helps within your own data set. But what if you're dealing with a totally new kind of problem? Or you want to leverage work others have already done, like using those huge models? This brings us to transfer learning, right?
Right, and this raises an important question. How does it actually work? How do you transfer knowledge? Well, think of it like training a generalist model on a massive data set. Maybe something like ImageNet, millions of images, cats, dogs, cars, everything.
Okay, so it learns general features about the world.
Exactly. It learns foundational visual patterns. Now, let's say you need a model for a specific task, maybe identifying particular types of, medical scans.
Which you probably don't have millions of examples for.
Probably not. So instead of training a model from zero, you take that pre-trained ImageNet model as your starting point. You then fine-tune its existing knowledge for your specific medical imaging task.
Fine-tune.
It can vary. Sometimes you might freeze the early layers, the ones that learn general features like edges and textures, and only retrain the later, more task-specific layers. Or you might retrain the entire model, but very gently, with a much smaller learning rate, just nudging it towards your new task.
So you're essentially leveraging potentially millions of dollars and hours of training someone else did.
That's the power of it. You don't need to be Google or Meta to build really good AI anymore. You can stand on the shoulders of giants, even with limited data.
It really does democratize things.
Okay, fantastic. One more. Active learning. This one sounds interactive. The algorithm itself queries a human for labels.
That's the core idea. It's designed for maximum efficiency when labeling is expensive or time-consuming. The goal is high accuracy with the fewest possible labels.
How does it decide what to ask for labels for? It's an iterative process. It starts with a small labeled set, like the others. Then, instead of just randomly picking more data to label, the algorithm intelligently selects data points from the unlabeled pool where it's most uncertain. The The points it thinks would give it the most information is labeled.
Ah, the tricky cases, the ones it's scratching its virtual head over.
Exactly. Those are the points presented to a human expert. The expert labels just those points, and they get added back to the training set. Then the cycle repeats. Train, identify uncertain points, get labels, add them back, until the model performs well enough.
So you're focusing the human effort exactly where it's needed most.
Precisely. You get the biggest bang for your labeling buck, maximizing that precious human expert time.
Okay, wow. So let's pull this all together. What does this all mean? We've got weak supervision for noisy labels, semi-supervision for leveraging unlabeled data, transfer learning for building on existing knowledge, and active learning for efficient targeted labeling.
It means we have this powerful toolkit now. These techniques collectively tackle that huge bottleneck of data, labeling the cost, the time, the sheer impracticality sometimes.
Right.
They really enable sophisticated machine learning, even when getting perfect hand-labeled data is difficult or just not feasible.
So it makes advanced AI much more accessible.
Absolutely vital. It opens the door for more organizations, more researchers to tackle complex problems with AI.
It really makes you think, doesn't it? If this bottleneck of labeled data is significantly reduced or maybe even overcome someday, what entirely new possibilities open up for AI? What kinds of applications could we see that just weren't practical before? Something for you all to ponder.